And for all the satellites that are on that region that's communicating through that part of the ionosphere, this is a problem, and you lose significant amount of data. It may happen at a very critical time, like for example in spacecraft landing or taking off. It needs accurate positioning information. It is very important to benchmark and monitor and model when this happens in certain regions. So this appearing and disappearing of these type of bubbles in the ionosphere may be temporally. I mean, at a certain time of the day they appear, or in certain region they appear, or in certain solar activity they appear. So how they appear over here when we are receiving signal, this is the task for us to understand, so that we can benchmark this information for us. So how we calculate delay? Basically, when any radio signal goes through the ionosphere, we consider that there's a virtual tube along the ray path, all the way from the satellite position to the position where the signal is received. This is considered as 1 meter square tube running along the ray path and full of electrons. So what we do, we actually try to integrate this tube and try to calculate how many electrons are along the ray path when the satellite is sending the signal and we are receiving it when it goes through the ionosphere. Okay, this is called total electron content. Since it is a slant calculation between the receiver and the satellite, we call it slant total electron content, or S-tag here. We put it into a simple formula and we get how much delay, this ionospheric delay or ionospheric range error, is being produced at that particular time and that particular frequency. Okay. So this is how we understand how ionosphere can be disturbing. This number is bigger when ionosphere is more intense. This number is smaller when ionosphere is less intense. So for example, slant tag along the ray path can be very small at early hours of night of the morning, like 4 a.m. or 5 a.m. But the same slant tag can be a large number during the daytime, like for example 1 p.m. or 2 p.m. local time. So the delay in the signal is different, and this has to be understood while we are receiving the signal, since we are calculating the position accurately. Since this is a slant calculation, what does it mean? It means that while I'm receiving the signal from a satellite, and satellite is flying at 20,000 kilometers, the actual position of the satellite may be beyond Saudi Arabia when I'm receiving the signal from it. So that calculation in its raw form may not be very helpful. So we need to map this information according to where we are receiving it, like where the receiver is placed. So we map the slant content to the vertical content through a very simple mathematics. And then we actually use this vertical total electron content in our calculation, and that tells us actually how much ionosphere is above us and how much delay it will produce at certain amount of time. So this is a basic calculation we do through GNSS. Now we have second instrument, ionosphere radar system. Ionosphere radar, when it works, we use it for every 15 minutes. And it produces an image like on the left side, a black background, and then we have different traces of the ray that return back. So basically, what is it? On the x-axis, we have the frequency. So these radar systems, they start sweeping frequency when they start operating from very low 1 megahertz frequency and going up to, they can go up to 30 megahertz, but we operated, since the solar activity is low, we operated until nowadays 16 to 18 megahertz. And we can still get a very good image of the ionosphere. On the vertical axis, we have the height. So each pulse that we send vertically upward, it reflects back from different heights. And that is actually the information about different layers around in the ionosphere. So if we actually look at this picture at a different way, in a more artistic way, on the right side, we can see that a typical ionogram looks like and gives us information about electron density profile. And all the anchor points that we get from the left side, we actually try to plot it on the right side to make a complete electron density profile. This profile tells us at what height how the electron content changes from very low 100 kilometer or 90 kilometer where the ionosphere is really taking impact and going up to 1000 kilometer. What does it do? It gives us basically a ground truth to verify any other remote sensing information that we are collecting through satellites, through GNSS receiver, and any other way, so that we know that whatever we are calculating and processing through GNSS data, we have ground truth to tell whether we are looking into the right numbers or not. So these these instruments are they can verify each other very well when they are installed at certain place. Now, what we have done up till now, when we were planning for it, the first desire for us to know what is already available. So if I take you to the picture here, even before we were present, we see that there is only one possible and closest data point available, which was in Bahrain. This Bahrain receiver is basically installed at Air Force Base, and it is installed for American Air Force, and they use the data for our purposes. But a part of the data which they share would have helped us. So we actually started downloading the data from their repository, and we started trying to understand what we can expect when we install our instruments. So what we did, we took the data. This receiver has been operating for tens of years. So we took data from them on one full solar cycle from 1998 to 2008. And we try to understand basically how much error we can expect in different solar activity in different seasons above our sky when the radio signal goes through the ionosphere, when it gets severe and when it gets easy to deal with. So in the picture on the right, each curve is representing one season. Okay, and one season along 10 years of time from 1998 to 2008. And what they are representing the ionospheric range error in meters. What is ionospheric range error? It's we can understand it simply as if we open up our receiver and we are only receiving the GNSS signal, and how much error we can expect while we are receiving signal from a GNSS satellite is the ionospheric range error in meters. So we can expect that we are 20 meters off in a peak time, or we can few meters off in a normal ionospheric time in different seasons. So what we come up with is that usually when the equinox time is there, the ionospheric error is large most of the time, except for the low solar activity, when almost we have the summer season, which is producing the largest error for the ionosphere in receiving the signals. So this is kind of a long-term study, collecting data and try to understand what may be expected in terms of ionospheric range error using a GNSS receiver. When we installed our receiver, we immediately try to compare it with similar instruments along the same latitude region. Okay, so what we did in these two graphs on the right side, you see the x-axis is going from minus 180 to plus 180 longitude. So we fix our latitude, which is around 20-25 degree latitude, and we try to collect data from all possible receivers around the globe at this range of 20-25 degree latitude. And you see there are several receivers. SH-J1 is the receiver installed at Sharjah. BRH is receiver installed at Bahrain. And then you can see the longitudinal region. The left side are either in Africa or North America, and the right side ones are in Asia. So we basically are, and we did this study at 2 times. At very quiet time, when local time is 5 a.m. Try to benchmark the quiet time ionosphere, and at a peak time when the local time is 2 p.m. and try to benchmark the ionosphere at that time. And we see that we are we got all the calculations very close to Bahrain. It means that whatever we see, Bahrain receivers see the same. So it is linked to the previous study, like whatever we benchmark through Bahrain receiver for a solar cycle, we can expect same results for the Sharjah. And then at the same time, we can compare ourselves how we are performing compared to the West, the African or South American or North American region, or East, the Asian region. Usually we found that the African region have larger error in terms of ionospheric range errors compared to the Asian region. So this is another very important result that we published in the conference. Now, when we started receiving data from the GNSS receiver, it's not only giving us the information about the range error, like positioning error, it also tells us about how we can look at the irregularities in the ionosphere above this region. Normally, when the signal is disturbed, passing through the ionosphere due to irregularities, we call this irregularity as scintillation. So scintillation does what? It actually stops signal to go through smoothly, and sometimes either we don't receive it signal or we receive it in a disturbed form. So the study we did on the right side, for which the plots are plotted, is that we try to understand if the scintillation occurs in the low solar activity, because when we installed the receiver, it was 2019, 2018 autumn. And since then we are receiving the data. So we want to make sure that in low solar activity, when we are installing the receiver, whether we see scintillation, whether there are some patches in the ionosphere. Number two, we would like to understand at what time of the day they are severe, and what are the main what are the patterns that we can expect from our region, so that we can benchmark this information as well. And on the right side, clearly on all GNSS signals, starting from GPS, the first 3 signals from GPS, the next 2 are from Russian GLONASS, and then the last 3 are from Galileo, from European satellites. And all satellites give us the same benchmark, that the scintillation occur in Sharjah. It means irregularities are present in the sky of Sharjah that disturb radio signals, and all are indicating the same time period, which is 3 p.m. to 6 p.m. just before the sunset. So this is the time when our signal are most expected to be disturbed, even in the low solar activity time, which is 2019-20, the current time. So this is a very important result. But the thing is that we had to understand why it is happening in so low solar activity. What is causing this to happen? So we took another point of view of the same information. So what we do from what we receive when we receive the signal, GNSS signal from the satellite, we are actually doing type of remote sensing, which is called ground to space remote sensing. But the same information can also be acquired through space to space remote sensing. And while we are doing it for the atmospheric studies, we call it radio occultation. In this radio occultation scenario, a GNSS signal is sent and received by a LEO satellite in orbit, and they scan the ionosphere, upper and lower part of the ionosphere, and produce a profile of upper and lower atmosphere. It includes many parameters. The most important for us has been the electron density. So on the right plots, the plots D, C and D, we try to understand the vertical structure of the irregularities that we can expect in the ionosphere. And on the plot C, on the top right, you can see that one is the global view, and the one is the Sharjah view, which is just selected the very close by events in Sharjah. And we can see that in global view, we have two major times when we can see we can expect, two major regions of ionosphere we can expect the disturbance coming from. One is around 100, 110, 120, where bulk of the information are piled up. The second piling up is around 300 to 400, which is the peak region of the ionosphere in terms of height. However, for Sharjah, we did not see much of happening in the 300, 400 region, but we have much of the disturbance coming from the lower region, which is 100, 110, 120 altitude, and which is shown here in the plot D, where the percentages are plotted. So how the percentages are actually happening, considering the altitude information, and most of the disturbances are going along at the region of 100, 120 for both global and Sharjah observations. Now, the second step, what we did is that we tried to understand at what time they are occurring. So the plot A here, it is showing that bulk of for all the altitude information is embedded here. It is telling us generally most of the time it is starting from the midday, which is noon, and going along up till midnight. So in 12-hour region, it can happen anytime. Okay, when we separate out the information about altitude, so all the information above 150 kilometer altitude and all the information below 150 kilometer altitude, we see that the below 150 kilometer altitude is exactly lining up with the pattern that we have received above when we were receiving data through Ionosphere. So here, which is the previous slide, we see that on Sharjah, we observe the scintillation disturbance in the radio signal at time between 3 to 6 p.m. And here in this plot, we can again see that in Sharjah, below 150 region, the scintillation disturbance occur between 3 to 6 p.m. most of the time, and sometimes after 8 p.m. But the significant time is always 3 to 6 p.m. So now what we have benchmarked here, we have benchmarked that the main disturbance in the radio signals coming from the lower part of the ionosphere, which is 100, 110, 20 kilometer. Plus we know now that what time it is happening, it is most likely happening between 3 to 6 p.m. Now the next step is that what is happening at around 110 kilometer, that is this is making this thing, this disturbing signal at this time period. For that, we went to the Ionosphere and we start combining data from the Ionosphere to the GNSS receiver. The plot on the right are actually it's actually plotting the information from a layer which is from the Ionosphere, which is called sporadic E layer. Sporadic E layer is observed by the Ionosphere when there are some extraordinary events happening in the ionosphere, like for example solar storms or any other disturbances. But normally in the low solar activity, it's not present at most location of the world. What we observe is that normally this ES layer is appearing in the ionosphere at 110, 120 kilometer region. When we start comparing the data from the ionosphere, which is the yellow curve here with respect to the time, and also the data from the GNSS receiver, which is the red curve and the blue curve, we see that they map almost absolutely, they are very similar in terms of the time of the day, at what time it is peaking and what time it is going, having a trough, and also the way the intensity changing at certain level. I mean, so how, when the intensity is going up, when the intensity is going down, and at what time of the day. So from here we got our second answer, is that the disturbance in the ionosphere is basically present due to the presence of ES layer, an extraordinary layer in the lower atmosphere, the lower ionosphere, which should not be present in normal time. And that's why we see the irregularities are occurring even in the low solar activity over Sharjah. And since it is a very different, very important result, so we were able to publish it again in the journal paper. But now the next question is, why ES is present in low solar activity? I mean, we have to understand why for the next step. So one of the very, very common answer to this is that the this ES layer is present at at a certain geographical location because of the burning or ablating meteors. So these meteors enter into the upper atmosphere, they burn the heavy metal oxides, they stay there and they sink down to the altitude of 100, 120 or 130 kilometers, and they stay there for a longer period of time before they finally disappear. While they are there, they are making a layer at the 110, 120 kilometers, which actually is can be caught by the ionosphere as an ES layer, which we are actually seen is creating the disturbance. And this is a very common understanding that throughout the world, the larger the meteor flux at any location, the larger the intensity of the ES layer. However, when we started combining data, luckily we have this MMN network, meteor monitoring network, and we have 3 towers, one of them installed next to the ionosphere. So it was a really good opportunity for us to test at least this thing, that why ES is present and whether it is due to the ablating meteors or not. When we combine the two data, starting from May 2019, when the ionosphere was installed, up till the April this year, 1 year data from the meteor counts and from our ionosphere. So the red curve is the monthly meteor counts, and the blue curve here is the average ES monthly. But surprisingly, these two results comes out as opposite. Means that when we have more meteors in the sky burning above the sky in the atmosphere, we have less intensity of the ES present. And this is absolutely opposite to what has been reported in the literature, because most of the literature it is believed and proved that there is a direct proportion between the two. So it's a very important result also because it's a negative result and it is in contradicting clearly with what has been published before. So this is a very good opportunity for us, and now we have submitted this study for the review. Hopefully we will get some comments and see what comes up as a result of it. Up till now, the data shows that there is at our location in Sharjah, there is no connection between the meteor counts and the ES intensity. And with that, the question remains why we having this ES layer in the Sharjah in the low solar activity. So we have to look into another direction, maybe some other data sets we will do later on. Okay, apart from all these observations and benchmarking, it is very important that the data is useful. Whatever we collect data, we make sure that this is useful. And the one way to make the data useful is to incorporate this data into models. So what are models? Models are general are the software or simulations that give us a general view of certain place for certain parameters at certain time. And models can easily predict future, but they cannot predict, without any true data, they cannot predict accurate picture of the future. But when we assimilate data from the real instrument into the model, we may be able to create a good picture of a future or at present through models. So this technique is called data assimilation, and I also perform some data assimilation into electron density model, and I took collected data from all around the world and also from our station here in Sharjah. So this is done because we have to make sure that whatever we are doing is useful for the systems which are operating around the world. This study shows that when we incorporate the data into the model at different location around the world, so different geomagnetic latitude are shown on the x-axis, and the percentage of improvement of the model is shown on the y-axis, and the hollow circles here are showing the low solar activity calculation, means percentage improvement at low solar activity, and filled circles are representative of percentage improvement of model because of the data at high solar activity. And we see very different results, very surprising results in the lower latitude. So latitude starting from equator 0 degree up till the 30-degree latitude, wherever I got the data from the ground and embedded into the model to see the improvement of the model, the improvement at high solar activity comes out as larger than improvement at low solar activity. It means two things. It means that at low solar activity, models working very fine and they don't need much to embed it in terms of data. And the second thing is that in high solar activity, when we actually need to predict ionosphere more accurately because other systems are not working fine, we can embed the data into the model and predict them in high solar activity, what we can expect as the worst case scenario. At the other end, when we went up to high latitude, we saw opposite trend. In high latitude, we see that in low solar activity, models improve more. Data improved the model's performance better way compared to the high solar activity. So this is a way to test what we are doing and how it can impact the nowcasting and the forecasting, which is the main desire of doing all these activities. Because we call it space weather. Space weather is like we can compare it with the weather we have. We need to expect when to have rain, when to have high temperature, low temperature, storm here in order to do our normal life activities. Similarly, we would like to predict the space weather, since the space, our satellites, our astronauts, and any system in space is prone to that weather. So we have to make sure that we can predict the space weather as accurately as possible in order to safeguard them. Now, that is what I have, whatever I've talked about up till now is about what we have done and what we have reported in different studies. Now, as a next step, we are started disseminating the data from two instruments at least. One is from GNSS receiver. So on the left side, you see a GIF of the ionospheric map, which we are actually calculating using our GNSS receiver. You see the UAE map here, and whatever we have done is happening above the UAE. These maps can be generated one day after. So, for example, this map we can generate every day after the data is available after midnight. In the middle plot is showing the GNSS satellites flying above UAE and what they are experiencing in terms of ionospheric disturbances and calculation while they are flying over UAE. So which satellites are seeing a high intensity ionosphere and which of them are low intensity ionosphere can be get from their color, which they are changing while flying over the UAE region. The right side plot is the one-day summary of the critical frequencies we have collected through Ionoson. So this plot is available a day after. So I have got the latest plot for yesterday, for 17 November, showing how the critical frequencies ionosphere is changing, what is the complete picture of them. So it gives a very good idea from day-to-day variability of the ionosphere, intensity of the ionosphere. So combining these two data, we can make the model very effective. So this is what we are doing now, and what are the plans for the future. The first thing is that we have to develop a data center, because we are currently targeting two major dissemination bodies, which are a representative of the global data centers, which are, one of them is IGS, International GNSS Service, which collects data from all GNSS receiver around the globe and report them at one archive, freely available for all the researchers around. The other one are the Loyal Gyro repository, which collect the Ionoson data from different regions around the globe, and they also show it in their in the website for the scientists to use it for modeling and measurement. Another step would be to fully develop the SaaS website. So all these the tools which are working on, or the data simulations we are working on, we would like to present them, to place them online, so that people know about our data center, and they can take advantage of what we are collecting through our instruments. Another effort is going on to unify the GNSS data network around UAE. Up till now, different municipalities are collecting GNSS data separately, just like we do. We have been doing efforts to talk to different municipalities to actually make a combined data hub, at least at the level of United Arab Emirates, so that all the GNSS data that are collected inside UAE should be available at one place for all educators or researchers to take the advantage of. New research lines we are working on, sorry. We basically, since we have already used the data instruments that we have been operating, now we are going towards using more and more satellite data. The two of the satellite constellations which are monitoring the ionosphere are SWAM and DMSP satellite constellation, and they are actually collecting very valuable data that can help us. So we are planning to use them in near future in the current activity. Also, the next step for the ionozone would be to improve the resolution. At the moment, in low selectivity, we are okay to operate it at 15 minutes, but maybe in high selectivity, we may have to experiment it by operating it. But there are some issues with the interference, so we have to understand how we can do it safely. Data assimilation is planned, and as much as data we can share from us, that has to be part of the models to improve models. So that data assimilation in the models is going on. One step I have already taken, but I will do more work on this. And another thing is that the ongoing study with meteorite center, by understanding why the ES layer is present and whether it is connected to the burning meteors, is still going on, and we may have to do more studies to understand why it is happening in the UAE, and how we can connect these two research lines. These are the research publication only taking the data from our instruments and being published in the last couple of years, like 2019 up till now. And hopefully this number will increase as we go on and do more efforts. Finally, this is the team. You know about Dr. Ilyas, and then myself on the left second. Other three are my students, Gowadan, Abdul Rahman, and Sahar. They are, you will, if you if you're coming to see us in our workshop tomorrow, you will see all the three participating and conducting the Ionosphere workshop, space weather workshop with me tomorrow. So this is a small team at the moment, but as we are growing in research lines, we may need more people. So hopefully we will expand it in all ways in future, inshallah. So that's all by me. Thank you very much for listening.
Thank you very much, Dr. Mubashir, for this excellent lecture, for all the information. I believe your group is very active despite its small size. Hopefully we'll get more students and also more people working in the group in the future, inshallah. Yeah. Please, so thank you very much again. So let me open the floor if someone has any questions. Before that, don't forget that tomorrow we're going to have a special workshop dedicated to space weather. So please, you are invited to be an on-site to be on the first floor toward the west direction. So we have a special sitting because of the COVID-19. So I believe everyone will be safe. So please check out the program that we have on our website, and also I will try to send an email as a reminder to everyone for the students and also for our staff here at the academy. So please let me open the floor. If you have any questions, so please ask Dr. Mubashir. Just one question, Dr. Mubashir. You said we need to increase the resolution of the ionosphere. So what do you mean by increase the resolution? You are going to change the signal frequency, or to change the time lapse, or so how do you do it?
Actually, and how we are doing nowadays is to have since the ionosphere is not dynamic at the moment, we are just taking a picture every 15 minutes and try to see to connect it from one picture to the next picture every 15 minutes. But when the ionosphere is dynamic, we need also to understand the plasma drifts, plasma velocities, the direction of the plasma, how it enters and leaves, and that makes us a very effective modeling parameters. So there are specific experiments conducted when the ionosound is even run at every 2 minutes to see how the plasma movement is happening at certain geographical location. So some regions only do it for as a project. So, but as we enter into the high solar activity time, it will be very interesting for us to understand what is happening here in this region. So we may have a we may have to find a way to operate in high solar activity times, maybe in higher resolution in time, so that we can understand that missing parameters which we have not been observing up till now.
So you mean the resolution in time,
In time.
not in terms of adding another ionosound, or
No. What we can do in that term is that we have a spare receiver, so we can install it somewhere around in UAE,
yeah.
and have the oblique sounding of the ionosound, which is another very important factor which we can do. But even staying at the same place, if the ionosphere is more dynamic, just like we can expect in high solar activity, that would be a very good experiment. So even only one or two experiments, you can report a very good results and publish very interesting results, because of the lack of reporting from this region, we have a lot of opportunity. The more we discover, the more we publish. So this is another way, quantitative way to look at it.
Well, I have a second question. For the you talked about the bubbles that we have within our own ionosphere. Do you know of any system that can monitor those bubbles, the size and the presence, and how they behave depending upon the season? For sure, they are all related to the sun activity. So how can we monitor those bubbles more accurately?
Well, nowadays there's no actual way, because this is sporadic. I mean, you never know, because it's like a liquid. I just
Yeah.
it's flowing from one place to another place within no time, so you cannot catch them, and you cannot predict them exactly when they're happening. But you can benchmark them by doing the 3D tomography. Like for example, one D would be like we do ground to split remote sensing. So this make a screen, vertical screen. Then we have radio occultation that goes into vertical direction. So it gives the second dimension towards the location. And then we have some independent constellation that are mapping it in a third direction. So all these three directions would be put into models, and models should be act like they are cubes in the region. So rather than we consider ionosphere as one region, we have to divide it into small cubes, very little cubes, like 1 kilometer by 1 kilometer. And with each, we have to understand how many data points we have. And then we solve it by cube and build the whole ionosphere. In that way, we know exactly in which cube the concentration is high. It means the bubble is present, and how many of those cubes are there. So it means size of that bubble, and which cubes are empty or at a normal level. So we can see that that's a normal ionosphere. So that's the only way people try to do.
Great. Thank you. Please, any other question to Dr. Mubashar? Please.
Yeah, Dr. Ilyas, Dr. Mubashir, I would like to ask if you don't mind. Thank you very much, Dr. Mubashir. I have just noticed that your name is Mubashir, not Mubashir. It means promising, and the project that you are having is really promising. Is really Mubashir as well.
Thank you.
And yeah, thank you very much for the presentation, and I'm really proud of having such a lab in our SAS that can contribute the data to the world, not only within us, because that's such a
That's
positive
important.
is worldwide, not local. Thank you. Well, I
Yeah,
have two questions. The first question is, uh, you know, for telescopes and large telescopes now, they are actually using some kind of laser beams they send the atmosphere to measure and to graph the atmospheric changes and the turbulence. So can this system do the same role to measure that? So that can be entered through the system, through the computer to avoid and to do the corrections is number one.
yes, why not? I mean, I think they may be used, but since there are two things, there are cost or benefit analysis if that people do it. These systems cannot be installed easily, and they are very expensive to do. So, for example, with a huge telescope, such systems can be very helpful because obviously already a huge telescope can take a lot of fund, and once you build it, you build it. But if you have and these systems are limited in geographical region, so they can they can understand a small geographical region around that particular instrument. Installing such instruments would be very expensive around the globe. So it may be only done by a very as a very expensive project. So if they can do it, yes, they will really helpful. Like adaptive optics, you may be mentioning, it is very helpful in that case, and that may also be used for ionosphere. But the cost benefit analysis is very high, so maybe they are not very favorable to measure something that may or may not be there. I mean,
Yeah.
disturbance may or may not be there for there, and rather than geolocating those disturbances at the moment, we are trying to avoid them. So, for example, our study shows that we have the a likely time of 3 p.m. to 6 p.m. Okay, so people know that in that time period, this instrument may be less effective. So let's go to the another point of view. Let's take data from other instrument. So we are trying to avoid it. But if it is not very costly to geolocate those things, those ionosphere disturbances, then maybe we go into the direction of accurately geolocating them through different means. So one of them would be this, yes.
Thank you very much. Maybe especially if you increase also what you call the resolution in time or time intervals. Yeah, the other question, if you don't mind, the graph that you put the number of meters, if you remember it.
Okay, let me go.
Yeah, it was in the middle, maybe. Yes, this one. So, uh, how the number can be counted here in this one, daytime and
Well, this
nighttime?
is another.
Or if I understand, maybe I have not understood the graph itself, but this is my question: how can we count this number?
The graph is simple enough. I mean, you can see the brown line. They are the count of meteors.
Yeah,
And I since you know the in the bottom you have a very light, very thin line, brown line in the bottom. That
yeah,
are
I
that is
see.
the daily calculation. Okay, but when I want to show it as a big picture, I average them over the month. So the brown line here, only 12 data points, averaging the number of meteors counted by the MMN network. So I took the data from them. The blue line is the average sporadic E intensity. That is the megahertz, the frequency. On the left axis, you see the blue axis. On the right vertical axis, you see the brown axis. So the meteor counts are done by the MMN network, and we took the data from them directly. So they are the visual counts of the
Okay,
meteors.
okay. So this is
So the main point here that there is no correlation between the meteor count and the sporadic ELA's occurrence, and that contradicts what has been reported, as Dr. Mubashir says. So we need to explain that, meaning that we need more observation in the future to make sure that this prediction exists really, especially in our region. You mentioned something very important, Dr. Mubashir, about adaptive optics to be able to control, or to at least to monitor Earth atmospheric turbulences. This is what you do exactly with big, in order to overcome this twinkling. So I believe it would be good to look into it, to see how it can be applied into what you are doing in terms of research. So how can we do this, especially if this perturbation they do happen 9 times, so we can use laser technology at least to know how the ionosphere is behaving.
Sure. Why not? Yeah, I mean, but since there are very few around the world, so we have to see how we can correlate the data between one place, and if there are other instruments available to verify the data which we are looking into. So this is very important.
Yeah. Okay, any other question, please? Okay, so we thank
Yes,
Dr. Mubashir. Sheikh. Yes, please go ahead.
Assalamu alaikum.
Walaikum
Thank you,
salam,
Dr.
please.
Mubashir. Yes, just I want to ask about the laser using in the huge telescope sometime to see the condition in the atmosphere. Sometimes we see the laser is very, very sharp. And beside, there is a laser with has a form a zigzag. That give us the idea that if it is zigzag shape, that means the atmosphere is not good, or
Yes.
there is turbulence. And if it is sharp, is good?
Well, it all depends upon, are you doing optical observation or something else? Optical observation, yes, it is an indication, but something else for the ionosphere, maybe Dr. Mubashir can answer that, I don't know.
No, we haven't. I haven't used any data of laser, so I think up till now it has been extensively used for the optical corrections of the atmospheric turbulence. But for as far as the ionosphere concerned, I haven't come across with any study. So maybe this is something that can be looked into.
Okay, thank you.
Okay, I just joined the class, right? Appreciate it. We see on the number there. But I go to.
Sorry, I cannot hear you. Can you please?
Strange, because I've unmuted the. Yes, now you can hear me, right? Can you hear me now?
Yeah.
Not
Yeah.
excellent. Not excellent.
Okay. Maybe. Yeah. What about now?
Yes, please.
Yes, great.
Yeah. It was only this. I had a class, so I could not join you. We just finished the class. But my thought because I just seen what you're trying to do here. What about the if you use the infrared to monitor the turbulence?
Depending upon what it's a lower atmosphere turbulences may be mapped, but upper atmosphere usually these turbulences are because of the free electrons. So basically we looked into the radio frequency because they are the most instruments or the most means the means who are experiencing this thing. So we are not doing any direct calculation. We are actually trying to do a remote sensing of the ionosphere. And why we do it? Because we compare it as a normal or a disturbed thing. And that's where we get actually calculation about whether there is some turbulence or disturbance present in the ionosphere or not. Like, for example, GNSS signal goes through the full ionosphere from 20,000 kilometers, satellites flying up till the ground. So we actually know because of the signal fluctuation at certain heights that this link is disturbed. And that's how we think that this is the position of turbulence. of the ionosphere, but there are no actual means to exactly pinpoint where they are. For infrared, I don't know if it is disturbed when it goes through the ionosphere. If infrared faces some difficulty, some turbulence, then only it will be helpful for us to do the remote sensing through the infrared. But now nothing has gone through from. I mean, I haven't studied anything, any paper or any published research that uses infrared to mark the turbulence in the upper atmosphere, in the ionosphere.
So I'm just thinking about this. You can measure the temperature, basically.
Well, you know, for the infrared, so you know that Earth atmosphere at 9, 10, 11 kilometers because of carbon dioxide, because of water, radiation is absorbed. So, and this perturbation in the atmosphere, they do happen 90, 100 kilometers. So I believe it won't be logical to use infrared radiation to study these perturbations. So there must be something else.
You mean it will be absorbed completely?
Yes. You observe nothing from ground surface. Okay, so thank you very much for Dr. Mubashir, for all who have attended. So we appreciate your presence, your support, and also we thank all those people who have asked questions, and hopefully we're going to benefit more. So tomorrow there is a special workshop to space weather. It will be on site, Academy for Assimilation Science and Technology on the floor. So we have a special setup to keep us safe, inshallah. So please, you are invited to attend tomorrow. I believe the maximum seat is 30 persons, first come, first served. Otherwise, you bring your own chair from home. Okay, thank you very much.
Why? Just I'm asking why you don't do it also part of it online. Like you just broadcast your, so people if they cannot get seats, they can just follow.
Yes, we'll do the broadcasting on YouTube live. Yes, we'll do that.
Okay, good.
We'll do that. I will send email about it.
Yeah.
Yes.
Okay.
We can do that.
Okay, thank you.
Okay, thank you very much for all. So see you tomorrow, inshallah.
Thank you very much. Thanks a lot.
Thank you.